Uh, Welcome back to the channel AK Apologics. In this video, we are going to discuss about the Verilog HDL, that is part 3, ASIC Design Flow. We have to discuss this point because from this only we can able to understand how we are going to work and what we are going to work and why we are going to work. What is the procedure, step by step procedure I'm going to explain in this class. And in the next part also I will explain some of the basics, and from the fifth part I want to discuss the Verilog HDL. Okay, from the fifth part I'm going to discuss the Verilog HDL that is related to the concepts. Okay, so till then you have to be very patient, and I recommend you guys to watch these first four videos, 2 to 3 times, because you guys don't know, right? It means when you are going to do, then only you guys are able to know, right? So I'm just explaining what is the procedure. Try to understand, okay? You guys watch these four videos 2 times, okay? Watch these videos 2 times. In the beginning you start the lecture, and after completion of this whole series you again watch this uh, first four videos one time. Okay, so let's begin with the video. In this topic we are gonna discuss about the let me let me yeah, what is VLSI, and we want to discuss about what is an ASIC. Okay, and we're gonna discuss about ASIC flow design flow, and we're gonna discuss about stage one in ASIC design flow, which involves requirements, specifications, architecture, and stage two in ASIC. It is stage two. It's I didn't print it right. It is stage two. Sorry guys. Yeah, stage two, and then the stage three validation. Okay, these things we are gonna discuss about. Okay, next we are going to see the next. Let's begin. What is VLSI? So VLSI stands for the very large scale integration. Very large scale integration. It means we gonna integrate millions of transistors onto a single chip. In this square area, we gonna impose or we gonna integrate millions of transistors. Millions of transistors. Okay, we gonna integrate those transistors, and also we gonna make connections between them, right? So we gonna integrate the transistors. That's the point. Okay, in this small amount of area. Okay, like this we're gonna integrate inside the chip. Okay, so which is a technology used to create a integrated circuit. Integrated circuit means the IC. IC will be seen, will be look like this. There are so many types of like ICs, like dip IC, and dip means the flat type IC. Dip means the dual inline pins. It means there will be two lines of pins we're gonna place. That is, this side is one, right, and this side is other pins will be there. Those will be in straight to this pin is the first pin. This one is straight towards the this pin. It means it is called as inline. Okay. So next we're gonna combine thousands or millions of transistors into a single chip. That is meant by the VLSI. VLSI, yeah, let me erase. VLSI has evolved the electronics industry by enabling the production of compact. All we are going to do is the design into the compact size. Previously, the computer size is in the room size, this much size. The computer is in the size of room. Now the computer is become the if you are going to take it as room, and previously the computer size is this much. Okay, so now the computer becomes this much. So this part, right? This much. It means the size is reduced, right? So the main aim of VLSI is to reduce the size and make the device compact and powerful. Okay, powerful in the sense it should be very speed. Okay, So previously the computers are very very slow and they are very bulky. So to reduce those things, our main VLSI aim is to reduce the size. It means to reduce the device size into the compact. Okay, nowadays the mobiles are also compact, and nowadays the CPU. So if you are going to see the Mac M4, M1, there is the box, right? This much box is there. Okay, very very small box, like our lunch box, right? So those are using, right? So what I'm trying to say is the main aim of VLSI is to compact the size of the device and powerful in the sense it should be work very very fastly, and the major thing for anything is low cost, right? Low cost. Okay, memory chips and uh, low cost microprocessors we are gonna build using the VLSI technology. Memory chips, digital signal processors, and other advanced electronics devices can be done using the VLSI. Uh, why VLSI only means the to have it in a compact size, to have those devices in a compact size. Okay, to have those devices in a compact uh, size. Okay, let me discuss next. So as of now, 2020, at the time of 2020, the scale of integration in VLSI has reached nanometer level. Nanometer means uh, nanometer processor. It means 10 power minus 9. It means that much of small will be there. It means that much of small devices will be there. It means nanometer it means the if you're going to take the MOSFET, this is a N-channel MOSFET. The the distance between the source and drain is in terms of nanometers. That's the meaning. Okay, the process level become into the nanometers. Technology in the sense the distance between the uh, drain and source. Okay, with feature size of order 7 to 5 nanometers. What is this 7 to 5 nanometers means? The distance between drain and source is either maybe 7 to 5 at the time of 2020. Now the size is 3 nanometers. Now at present the size is 3 nanometers. Okay, yeah, allowing for the integrations of billions of transistors on a single chip. Now we are going to integrate billions of transistors. Previously we want to integrate millions of transistors. Now we are going to integrate billions of transistors. Okay, yeah, next. The latest processor and integrated circuits are being manufactured using 7 nanometers and 5 nanometers process. Now it is become to 3 nanometer technology. Okay, so this is the previous data which I have collected from the various sources. Okay, enabling greater performance and so power efficiency. Power and efficiency means we are going to use less power. Okay, so we are going to use power effectively. Okay, yeah. So the next thing is what is ASIC? ASIC is a application specific integrated circuit. Application specific. Note this point. ASIC is nothing but the application specific. It means uh, that integrated chip circuit is specified to one application. For example, if you're going to take the chips in laboratory, if you have the multiplexer chip 74138 multiplexer, okay, the that chip is always uh, does the multiplexer operation. It gives result as multiplexer operation, and there is no programmability once it is programmed. Okay, it is fixed, right? So when we are going to write impose that code into this impose and manufacture this chip, we can't able to reprogram this chip, right? So it means this chip is particularly specified to the application mux only, mux operation only. We are going to take and IC, there will be four ICs, right? Here there will be one IC, and here there will be one IC, here will be one IC, and here will be one IC. All these four ICs, every time all these four ICs are work as AND gate only. So we can't able to make this four IC AND gates into the OR, right? By programming. So we can't able to program, right? This particular IC is specified to do the AND operation only. So Application specific integrated circuit means after we have designed the code, after we convert into the layout and all the integration have been done, and the connections between the transistors also has been done, we can't able to reprogram this particular chip. That particular chip is called as application specific integrated chip. It's a type of integrated chip that is designed to perform a specific task. It means only one task will be done, okay, which is already predefined in the program, and for with respect to that program we will generate layout and we will make the interconnection. Okay, we can't able to change the functionality of that particular chip. Okay, yeah, it is customized for applications unlike general purpose IC such as microprocessors and microchip memory chips. Okay, yeah, let me there is this, yeah, it is customizable for the particular application unlike general purpose IC such as microprocessor and microchips. Okay, so it is customizable means we can use the FPGA and test the uh, things whether the processor is working or not and my memory is working perfectly or not. We can use the FPGA and we will test the whether the codes of these are working or not. Later then we will generate the layouts and all this stuff for the big circuits like microprocessor and memory chips. Okay, it's a typically used in high performance applications because ASICs give high performance because it is specified to only one specific task, right? So it give a high performance. So we are going to use this in high performance applications. Such specific processing requirements need to be made, such as in networking and telecommunication and consumer electronics. These are the some of the examples where we are going to use ASIC chips. ASICs are designed and manufactured for a specific customers because we have to perform only specific task, right? So is only is manufactured for the specific customers or application. In the sense, if you are going to have some need of AND gates, then using ASIC we only made AND gates and give to you. Okay, so if some other person need OR gates, using ASIC we make OR gates and give you. Okay, so the that particular chip is only yeah, that particular specific is fixed, right? So we in these ASICs we can use digital, analog, and mixed signals components on the single chip. Okay, using ASIC, if we are going to make manufacture any chip for a particular task, then we can able to use digital, analog, and mixed signals over there. Okay, next, yeah, next the thing is ASIC design flow. Here comes the main part, ASIC design flow. A typical design flow follows a structure shown below. Can be break down into multiple steps. We are going to break this ASIC design flow into multiple steps. Some of these phases have happened in parallel and some sequentially. In the given steps, we gonna make some of them. The steps are being parallelly. It means we are going to do those steps parallelly, and some of them will be done sequentially, one after another. We'll take a look at how typically project design cycle looks like in the industry today. Okay, let's see. Okay, yeah. So, uh, this is the first stage where we collect the requirements from the user or the client. Usually we call them as client. We collect the requirements of them. Okay, what they needed, how whether they need a low power consumption device or whether they need high cost device, whether they need high duration, high reliability. All these things we will ask them and we will note it down. Product requirement or specifications. Okay, we will ask product requirement specification what they are need, whether they need microprocessor having to what type of instruction set, and all this stuff will be taken by the user from by us. So we will ask them and we will take and we will design. We will also ask them how the architecture should be. It means the outer body how it should be and the inner components what we are going have to use. All this stuff we will ask them. Okay, yeah. So requirement, right? It means collecting requirement, right? Let us discuss each one of them in detail. Okay, all these three things. Okay, collecting requirement, stage one. A customer of semiconductor frame is typically some other company who plans us to use the chip in their systems or end products. It means that the clients who are going to give us the specifications, they are from some other semiconductor frame or the company, typically some other company, okay, who plans to use our chip. Because why they are giving to those specification to us is because they want our chip to be used in their product. It means designing the chip by themselves on it took a very large time. So most of the companies, like product based companies, will give some of the small projects or the for the service based companies, okay, product based companies will give small projects to the service based companies. Product based, there are two types of companies: product based and service based. Product based companies where the end product will be come to you, will be designed, and where service based company is the company which does the work for the product based company. It means product based company will assign some of the work which is needed in their project. Like they will assign some work like design the code and verify and give it to me, like this type of works will be there. Those will be assigned by the product based company to the service based company. Then service based company does this work and give it to the product based company. Then product based company use that design and will uh, generate the IC. Okay, this will be done. So the product based company will give the instructions to the service based company. That is the thing here given. It means they need requirement, right? Whenever the service based company is doing the project or the client, even though the product based company will get the uh, specifications or the requirements from the users. Some of them they will have a selective amount of users. They will give some inputs also. So from and the technical team of the product based company also give the requirements. Okay, after taking the requirements, so requirements of the customer also plays an important role. So this is the point. See, I have told, right? There will be some of the selected customers. The company made them to use those their projects, and they will get a review from them and ask them how the design should be. For example, Rolls-Royce company uh, designs the everything inside the uh, car by asking the inputs of the customers, previous customers. They will ask, okay, there will be meeting for them, and they will ask what features do you gonna want us to add in the coming generation. They will ask like that. Rolls Royce company, I have listened that. Okay, so it's an important role in how deciding how should be designed based on the customer. Okay, customer in the sense our user. So most of the users some don't know aware of the devices, right? Who are having the aware of devices and who are going to use more amount of devices, more devices. From those people, the product based company will take the reviews, and they will ask you how do you know your design. They will ask like that, and they will write those points as and they will discuss with their technical team and will give you requirements to the team inside the product based company. Or if they wanted to assign that for particular work to the service based company, then the requirements will be given to the service based company. Naturally, the first step is to collect the requirements. What are the requirements based on the previous generations things, and estimate the market value. We will have to estimate that market value. It means the iPhone is having so much price, right? So every generation the iPhone is uh, will be changed, right? How it will gonna change? Because it is how the requirements getting changed, because it's the requirement of us only. It means the user will give the feedback, and the technical team of the company will add that requirements and will check if it is it necessary or not. All these things will be done, and all these should be related to the market value. What is that market value? It means iPhone has the huge market value, and Samsung also will be their huge market value. What if some of the company which having have any that much of market value and took the feedback from the customers, and if they add, the end product may give a and loss to them, because the company doesn't have that much of market, right? So even though they have, if they had the requirements taken from the users to their product, if the budget will be more, right, it means the cost will be high. So when the cost will be high, there is no that much of market to that product, then they will get lost, right? In that cases, the company won't add the features, even though they know what to add to the product, what not to add to the product, even though they know they won't add those things, because at the end the company should get the profit, right? So they, if they have the huge market, then they will make the changes accordingly if the budget is less. Okay, otherwise if the budget is high and they have no huge market, then the company sometimes, even though they have the ideas of better ideas, they won't proceed. Okay, so evaluate the number of resources required to do project. Okay, we must evaluate after getting also requirements, what are the resources that we already have to do the particular project, and what we have to obtain for this project that are not available with us right now, like that. Okay, next, another thing is specification. Now the requirements have been done, right? They will take the requirements on the company senior technicians and the customers, and they will again look for the what are the requirements, like that. Okay, specification. Now the specifications, the next step would be specifications collect that describes abstractly the functionality. After collecting all those requirements, next specification in the sense the functionalities, interface and overall architecture are to be designed. This is something along the lines like requires computational power to run imaging algorithm to support virtual reality. This is one of the functionality. This is also given by the user. Mostly this will be given by the users and technical team only, because they will add future related things, right? What is gonna add? We have to add feature. For example, nowadays WhatsApp added the status as story, and WhatsApp created some channels, right? This is the update, right? Similarly for hardware things also, there will be some of the updates. It means uh, some of the updates which will improve the particular design, which will improve the particular design. Okay, so next, requires two R processors with concept coherent interconnect and should run at 600 MHz. This is one of the specification. It means the client requires the ARM A53 processors with coherent interconnect, and this and should run at 600 megahertz. It is the clock frequency, right? So this is also functionality or the function specification. Okay, requires USB 3.0 Bluetooth and PCIe second gen interface. It means this should be these are should be used in their design. It means these are the specifications, right? So next, supports uh, 1920 by uh, 1080 pixels. It means this is the screen count, right? Display with appropriate controller. So these are all the things that should be used in that product. Uh, that must be used in that product. Okay. Next, yeah. Let me cook. This is so architecture. Coming to architecture, now the architects come up with a system level view of how the chip should operate. It means based on the requirements and the specifications. Once the company is okay, these are the requirements, these are the specifications that we have to use, and these are the things that we are gonna use. If the company fix like that, then the works goes to the architecture. Those information will be given to the architecture. In this, there will be architect, though they will come with the system level view of how the chip should operate. They will decide what all the other components are required. It means after the given by the specification, this particular components and this particular fastness and the requirements by the user, they will design a system level thing. So while designing, they will able to know that uh, whether those components will be useful or not. It means those components itself is enough or not, they will come to know. So if the components are much enough to do that particular thing, they won't add any components. If the components are not much enough to add, they also require some other component that they also include them also. So the architects also include them. What clock frequency they should run, how to target power and performance requirements. They are able to reduce the power and performance requirements by removing some of the modules which are unnecessary, or whose work will be replaced by some other module. If you are having to have two modules, if there are two modules in our design previously, after designing, architect have designed it. So if the work of module A can able to do by the B, then you should neglect the if you neglect the model A, then the power will be reduced, the area will be reduced, and the performance will be increased, right? Because we're gonna neglect one of the module uh, from the previously present modules, right? So like this, the architect should think, right? Yeah. They also decide how the data should flow inside the chip. They also think this, and an example would be the data flow when a processor fetches imaging data from the system RAM, executes them. So this is one of the example. Yeah. In the meanwhile, the graphic engines will execute post-processed data from the previous batch dumped into another part of memory and so on. So they have to think in this way also how data should flow, how data should fetches the image from the processor, and how the graphical engines will be execute post processed from the previous batch dumped into another part of memory. So all these things should be keep in architect mind. So this is one of the architecture image like this. Like this, based on the user input and the requirements and the specifications, the architects design this. Architects usually design this thing. This is an ARM processor, in which they have given ARM processor PCI protocol, right? So all this stuff, by taking all this stuff, the architects will design this. Okay. After architect designing this, there will be a stage two. We have to digital design. Digital design in the sense we have to write the code for this architects each and every block separately, and we have to integrate all those things, and we have to use some of the interfaces and all this stuff. Okay, the next stage two is digital design. Because of the complex nature of modern chip, it is not possible to build something from scratch, right? We can't able to build something from scratch. So if the particular module here, we are going to take this particular module, AHB bridge. AHB bridge chip is already designed by some other company perfectly with low power and low area and low low delay, then we can able to use that particular chip. So for example, this chip is already available in the market by some other company. So it is also very valuable in the sense it's work very perfectly and a very optimization level. So then we can able to use that particular chip in our design rather than designing this particular chip from the scratch, because already there is existence, right? So if you are going to start this particular chip which is already existence from the scratch, then our time will be waste. So we have to think about also that and market value, and also we have to think about the how much time whether the device is gonna manufacture. So we have to keep all these things in mind, and we have to decide whether we are going to do the full custom design or semi custom design. Full custom design is nothing but full custom and semi custom will be two things will be there. Full custom means nothing but the everything will be scratch. So all these particular models which are have separately will be designed from the scratch. Okay, it will take a long time. Whenever research is going on, professors or the scientists usually make this usually prefer this full custom design. The semi custom is nothing but it means among the available modules, in our architecture, if the some of the models are already present in the market with excellent performance, then using semi custom design, they will be replacing those modules using already available uh, chips. Okay, So they only write for the some of the chips which are not available, or which are available but with a low performance. They will usually make that chips only with uh, full custom, in the sense from scratch. Okay, so this is the thing. Next, I have discussed about this point, right? So some X company requires a FlashCon module to interact with other modules in automobile. They can either buy the FlashCon design. Okay, so already the FlashCon module is FlashCon design is already available in the market with a good excellent performance. Then they can either buy it. It means if they buy it, it will become semi custom. If they buy it, and the, it will become semi custom from other company to save time, to same time. So when we are going to buy that particular design, we will save our time, right? And effort or spend resources to build on one on their own. So when we are going to buy, the time will be reduced, saved, and effort will be saved, and money will be saved. How we won't assign any some other people to that particular work, right? So the money will also will be saved. So but the thing is, the performance will be medium, because we haven't designing the particular FlexScan module in our full custom, right? So we are already using that particular design which is already available. So using this particular design which is already available will may affect our performance. It means the perfect performance will be medium. It means to get the higher performance, higher speeds, you should use the full custom only. Don't prefer a semi custom. But using full custom, there is one of the drawback is long term. If the design is started now, after 20 years, the product will be launched. This much of time will be taken. But whereas using semi-custom, it will be in 2 to 3 years, or maybe probably in 1 year. Okay, will be the product will be come into the market. Also, it's not practical to design such systems from basic building blocks. So it is very difficult, right? Like flip-flops and CMOS transistors using these. So designing a thing in from the scratch level is very difficult. Instead, a behavior description is developed to analyze the design in terms of functionality, performances, and other high level issues in hardware description language such as Verilog and VHDL. So rather than from the scratch writing code for flip-flops and CMOS transistors, we have to describe that behavior, how the circuit is being worked, or the functionality of the circuit. We have, if we describe this, then it is very easy to develop the code. But the we can't able to do the optimization. To do optimization, we have to must write with in the code in the form of RTL or the gate level code only. So this is usually done by the digital designers. First, they will write the behavioral description. It means they write the code in the behavioral model, and later the if the functionality is okay, then they convert the code into the which model, RTL model or the gate level model, because using behavioral model you can't able to do the optimization. Okay, optimization is very difficult using the behavioral model, but writing the functionality of the code in the terms of Verilog or VHDL is very easy compared to the RTL and uh, gate level model, because using behavioral model we just need the higher level details of the things. It means if we just know the functionality of the design, then we can able to do the behavioral code. But whereas in RTL and gate level modeling, we have to know the each and every detail of that particular module, because we're using gates, how the gates are connected. Using gate model, we have to know the how the gates are connected, how many gates are there. Using RTL, we have to know about the equation which is formed by that particular given logic. All these things we should know. This is usually done by a digital designers and some kind of similar to the high level computer programs. It means using behavioral description is nothing but the high level computer program only, equipped with skills in digital, some skills in digital electronics. Okay, yeah, st- stage to still designs, because of the some complex nature of modern chips. It's not possible to build something from scratch. Yeah, if we are gonna build also, it will take long time. In many cases, a lot of components will be reused in the sense, this is the point I have discussed already. Existence model will be reused if the performance of that particular model is excellent. So even the performance of the particular model is excellent, the performance may get will be low, because we haven't done any research, right, on that particular model. We just took that particular model which is already available in the market. So it may affect the performance. Okay, say some expect. This is the point. I think this has been completed, right? Yeah, this has been completed. Sorry for the interruption. Yeah. So this is the thing. We'll write the code. We will take the models which are already predefined. Predefined. Now we have to write that code for that in behavioral model. Sorry, we will take the particular models for the components which are not already available or the performance is pure for that things. We will write a behavior description first. If everything is fine, the module is also working properly, then we will convert that particular code into the gate level or RTL level, and we will do the optimization, and we will do our required design by integrating all the modules, and we will get the our design. Okay, yeah, next. So this is the thing for a single port RAM. This is the module name. This is the module keyword. We must start with this while starting Verilog, and we must end with the end module. So this is the parameter. Parameter in the sense a constant value. We are going to give the address width of 16. Okay, the address width of the RAM, single RAM means memory, right? In the RAM, if you are going to have this, so if you are going to have this many of location, this if you are going to say this is the RAM, for each location we gonna use 16-bit address. For to represent all this, we gonna use 63-bit address. 16-bit address. If the first location is 133 1234H, it means the address of first location is 1234H. So to use to represent H in the sense hexadecimal, so we will represent each of the digit in this answer 4. 4 into 4 will be 16. Okay, so the data width is 32. 32 in the sense in this particular location we can able to show the store the 32 bits. Okay, in one particular location of the RAM single RAM port, we can able to show the 32 bits. This is an example I'm going to discuss. This is the specification, right? So we are going to use the 16-bit address, and data bit is 32, right? We're gonna use the single port RAM. We're gonna design the single port RAM. These all are the specification and our requirements, right? So next, we are going to discuss input class, which is a usually set the speed and synchronous write enable. Write enable means when we are going to write, we have to turn on this. Okay, yeah, the width input wide. Whenever the 16-bit address which will be ready, whenever the number is starting from the zero, the ending number should be -1, right? So the number is starting from the zero, the address width will be -1, right? It means 15 to 0 will be there. Uh, ADDR of 15, ADDR of 15 to ADDR of 15. If you're gonna count ADDR of 15 to 0, you will get 16 values. So we are going to minus that particular value 1. Okay. So why we are going to have 16 values when starting from the 0? Because we have included 0, right? So from 0 to 15 uh, there will be how many? 16, right? Because 1 to 15 will be 15 and 0 is other, right? So there will be 15. So we have to minus. Okay, next. Data in. Data in will be similarly data in will be 32. But 32 to 32 means here 32. 32 1 minus 1 means 31. 31 column 0. 31 column 0 means total 32 bits. So how 1 to 31 will be 31 and 0 is on some other extra bit, then it will be 32 bits. Okay. So we will represent like this because all these are input signals. Okay. Yeah. Output where D out will also 32 bit. Okay, there is D out also 32 bit. Next, so we have to end it. After model, we wanna use the hash to specify the parameters. Okay, this is the memory declaration of memory. It means what is this meaning is the data width will be 32 bit. It means the data width will be 32 bit. There will be one location of 32 bits. This particular location has 32 bits. 32 bits. Okay, in this 32 bits will be there, and the address with will be actually the address with is 16, right? We have a formula for that. 2 power the location for the location of the uh, for the how many locations should be there in RAM as a formula, that is 2 power of address width. Here the address width is 2 power, yeah, here the address width is 16, right? So the how many locations should be there will be formula 2 power 16. It means this is one location size. Similarly, we gonna have 2 power 16 locations. 2 power 16 locations. In the sense, 2 power 16 locations will be there for us. So each location can be able to represent using 16-bit address. It means if the first location is 000H, 000H, the location will be the last location will be FFFH, FFFH, because uh, F in the sense all ones, right? So because we gonna represent the locations in terms of 2 power 16, right, where 16 is the address address width, right? So I'm gonna explain one of the example. So this is the case, okay. This is specifications and requirements of the user or the client given to us, okay. Yeah, next we gonna use always at the passage clock begin. If w rate equal to 1, we should write the data, right? So enable, we gonna write memory of address, memory of ADDR equal to DL. So we gonna send the data to the memory of ADDR, which means we are going to send the data whenever the write enable is 1. ADDR in the sense the address, right? EDR in the sense the address, this is the thing. Here maybe here it maybe have or some other location, some 1 2 3 H also will be we can store by specifying that particular value in the ADR in the test bench. Okay, in the test bench we gonna specify those values. Okay, next we're gonna end the if we're gonna end the always block because we have started, right? We have to use begin and end if there are more than one statements, okay. Not only no, there is also no problem when we are going to use even only one statement, but most of the cases to use when more number of statements are there, more than one, okay. So read out data from the current address. So from the current address, if we are going to read out using the SN keyword, SN is nothing but the continuous assignment statement which is used in the RTL coding. We will discuss all this when coming to after from the fourth video. So D out is equal to memory of address. So we're gonna read that particular value whether the value is correct or not. So firstly, we're gonna send that particular value into the memory of address when the write enable is 1. So and the secondly, we gonna read that particular value which is in the memory, whether the data that we are going to push into the memory of address is equal to the DIN or not, whether the correct value is given or not. So we gonna read that particular value, okay, and then we should end the module because we have started the module with module, and we should must end the module with end module. Next. Stage 2 verification. After designing, we should verify, right? Should verify the design. So we have to write the TB. So once the article design is done, it is need to be verified for the functionality, whether given functionality is getting working properly or not. For example, a DSP processor is expected to issue bus transitions to fetch instructions from memory. But how do we know that this will happen as expected? So anything, for example, in this thing, previously thing, how we are going to know that particular value is the D value is same, the D value is pushed into the memory of address. How we gonna do by reading that particular value in this step, right? So whether this functionality is working or not, we should apply some of the input values to the D in, and we have to check the D out, right? If you are going to apply give the data one, here must be one, right? How we are going to check in the design code? We can't able to check it, right? We just write the functionality, right? To check that there must be a TB. So functional verification is required at this point, okay. Yeah, which is done with the help of video simulator. There are so many simulators which gives the waveforms and console output as that has capability to model the design and up to different stimulus. Stimulus in the sense different input combinations or the vectors or the scalar, different input cases. So this is the job for the job of a pre-silicon verification engineer. Okay, they will verify who we are going to verify that particular design. Pre-silicon verification engineers, simply known as verification engineers, are used to verify that particular design is correct or not by applying the TB or the test bench, uh, which contains different combinations of inputs, and we're gonna monitor those. Pre-silicon in the sense before starting the fabrication process. Yeah, this is the thing. This is the top model in the sense the TV module in which we are gonna instantiate our design in the sense DUT, design under test. We can able to call our design as DUT or the design under test. We gonna instantiate the our design in the TV because we gonna apply the inputs, right? So to apply the inputs, there must be a design, right? So we will call in the sense for our understanding. I am saying that we don't call. So we will instantiate that calling is called as instantiate. We will instantiate DUT in the top module or the test bench module. So there will be some interfaces. Okay, interfaces for the this is but this is the TV. This is the TV. This is the DUT. So we have to interface uh, DUT with TB. How we are going to interface by giving that particular values using dot A of A. In previous case we have seen, right, dot A of A and dot B of B, like this we are going to give, right. So it means we are going to assign the input and output values in the design uh, to the particular values of input and output in the TB. So for that reason we need the interface. There will be connections. I have drawn those. After giving interface, we gonna drive in the sense we gonna apply inputs to the design. Apply the inputs or the test cases that are going to sequencer is used to generate the this is active sequencer, this is passive sequencer. The active sequencer is and the passive sequencers are used to generate the test cases of the for the particular design to be tested. Those test cases will be given to the driver or the BFM, which is known as bus function module. Those test cases will be applied to the DUT. It means we're gonna check those input values by applying to the DUT, and we will get an output, right, through the interface. Through the interface we're gonna apply the input, we will get the output, right. Through the interface we will take it to the monitor. What does the monitor does is monitor is used to monitor what are the input and output values, what are the input values have been changed, uh, and what is the particular output value got for us by applying that particular input. So after all this, the thing is to we must confirm whether given design is correct or not. To confirm whether the given design is correct or not, we must have some reference value, right? Reference value in the sense we must have truth table. So in reference value, the actual values of that particular test cases which are being applied to the design will be available in the reference module. What will be available in the reference module? The actual uh, output value for the test cases which are being driven to the DUT. So while the sequencer will generate some input test cases, those will be driven to the driver driven to the DUT, right? So then the DUT will give some output, which means it is related to but that particular design output, right. So whereas in reference model the actual output of our design which we have thought in our mind will be there. So the output which is got by the DUT and the actual output which is the correct one in the reference module will be checked by the checker, will checked by the checker and display whether our code is correct or not using the scoreboard. Both the reference model and checker is called a scoreboard. Sometimes there is a scoreboard, some other model. The thing is, the sequencer is used to generate the different combinations of inputs. Okay, after how the sequencer will be generated? So we only giving the test cases the TB. So I'm for the sake of understanding, I am gonna say that. So we gonna write the sequencer code also. Sequencer code is nothing but different combinations of input. We gonna write in the form of code. So okay, there is no. This is not a hardware block. We gonna write code for sequencer driver interface DUT monitor reference module checker. For all this we gonna write code. So the sequencer purpose is to generate the input test cases. How it going to generate? We only writing the code. Okay, we only writing the code for the sequencer. So after that, the driver will drive the in those test cases to the DUT via interface. Okay, for driver interface and DUT we will write the code where DUT is the our design code, right? After applying those inputs, there will be some output. Is it correct? No. Is the correct? No. So that only we have to check, right? So to check that particular value, that is the actual output of our design, estimated design is also available in the reference model. The output now the output is got from the DUT, right? Both the values will be checked by the checker, and if the both the values are same, it will there is a scoreboard. Then okay, your design is perfect. You can proceed the next step. Like this, we will write some display statement and we will display. If the both the values are not equal, then there is a error, and it will show there is a error. You have to check it properly, and we will show the lines where the error is there. So this is the thing. So after this, verification should be done. This is a part also verification, right? Previously, to save time, reach functional closure, both the design and verification teams operate in parallel. So both the design and verification teams operates in parallel. How the design team will write the code for the design, whereas the verification team will write the code for the verification. Uh, Parallel where designers releases an RTL version. RTL version means one version of code for the design, and the verification team develops the test bench environment and test cases to test the functionality of the other RTL code. This is only I have discussed, right? If any of this test fails, any of the test fails, then it might indicate a problem with the design and a bug, right? So will be raised a ticket on that design element. So usually the design there will be some design engineers so usually write the code for the design and will give it to the verification engineers. The verification engineers will write the TB test bench which is used to apply the test cases to the design, and after applying those test cases, if we have any errors or if you have noticed any unusual things, then the verification will be engineer will be raise a ticket to the design engineer using the Jira application. Jira, there will say some of Jira will be there. So using this, the verification engineer will raise a ticket to the design engineer. Then the design engineer will check whether the uh, code is wrong, and the code is wrong. Okay, we have to change it, and the engineer will change it and again send it to the uh, verification engineer. The verification engineer is again verify that code, and if there is no error, then it will go to the next process. Otherwise, if there is any error, he again raise ticket to the design engineer, and the design engineer will now raise the uh, take it to the architect, and design engineer will work in the parallel and architect will work in the parallel, and verification engineer is also works in the parallel. Okay, yeah, this process goes until there is a good level of confidence in the functional correctness of the design. So this is the point I have discussed, right? Yeah. So next, logical synthesis. After everything is good, everything is fine, we don't we don't need the TV. It means the TV work is have been completed for the design. So after the our functionality is correct. So TV is just for the applying inputs and whether to check the output is correct or not. The design is correct or not. If the design is correct, now the design is should be connected into the synthesis schematic gate level at least. Okay, the design will be converted to the symbol. Okay, simply I'm gonna say symbol. Okay, You're gonna convert to the symbol like with real elements like combination gates and flip-flops. It actually not convert into the gate. There will be some code. Okay, this particular the conversion of design code into the symbol or the schematic hardware schematic is known as the synthesis. Okay, we are have to know that with the design we are happy with the design in the sense the design code is okay after performing verification using the TB by the verification engines. Now it's time to convert this into the hardware schematic with real elements like combinational gates and flip-flops. This particular step is called as synthesis. Okay, logical synthesis tools. Yeah, logical synthesis tool enable the conversion of RTL description into HDL to a gate level netlist. Okay, hardware logical synthesis tools will be there, though they will be converted the hardware description RTL description in HDL to gate level netlist. The netlist is nothing but a description of this circuit in terms of gates and their connections. Netlist is nothing but the description of gates. It is not the hardware symbol generation or not. It's like a look like a gates. It's not like that. So it's an hardware description in which they contains how many gates will be there, how many flip-flops will be there, what are the types of flip-flops will be there, how the whole components will be connection, how the combinations will be look like. So the thing is like it will generate like this. After completion of this, after completion of the design code and verification if the design code is perfect, we're gonna give design code to the logical synthesis, then logical synthesis will generate this. It means it will shows the thing right the flip-flop is required and uh, the AND gate is required and the connections it means is showing this here in this the what are the connections for what we have to connect like this all this stuff will be shown. Okay, yeah, then logical synthesis tool ensure that netlist means timing area. It means the it also sees the things like the design code is matching with the timing and area and power specification which is given by the user in the beginning. The user himself or the client will be given. User in the sense not us here. The client it means the product based company or the service based company or the person who gave the deal or the project to the company. Okay, they will give the timing and area and power specifications. After converting the design into the logical synthesis gate level netlist using the logical synthesis simulator, they have to check those timing, area, and power specification. Typically, they have access to different technology node processes and libraries of digital elements and can make intelligent calculations to meet all the different criteria. There are so many libraries and calculations engines for doing this purpose for checking whether the power and the timing area are matched or not. These libraries are obtained from the semiconductor fabs. That means these are given by the semiconductor fabs to the service-based or product-based companies that provide data characteristics for different companies like rise, fall times. It means they will provide what is the rise time, fall time should be there. It means libraries provided by the semiconductor fabs will be provided. What is the rise time, fall time, what is the rise time, fall time for flip-flops, input, output time for combinational gates, etc. These will be given by the semiconductor fabs. Fabs in the sense here also product-based company. Product-based company in the sense uh, fabs in the sense those who will make the chip and who are going to make the chip physically. Though those will be called as fabs. Fabs in the sense fabrication industries. So water will be there in those libraries. There will be like what is the rise and fall times for flip-flops, input and output time for combinational gates. All this stuff will be there. Okay. Yeah. Logical equivalence. The gate level netlist is then check logical equivalence with the RTL, sometimes a gate level net verification. After we again do the verification by generating that schematic, we will perform again. Verification is performed where verification of certain elements are not done once again. The difference being at that this is time it's gate level and is at a lower level of abstraction. So we will do all the design code and all this stuff in behavioral firstly. If the gate level at least using that behavioral model is okay, then we will convert that particular code into the gate level modeling. Okay, why? Because using behavioral we are going to specify only functionality, right? So using only functionality, if you are going to specify the design, then the synthesis output hardware schematic will be very complex because you haven't mentioned any internal details of that particular module, right? So but even the functionality will be achieved by us, but the circuit complexity will be more. Now we have to reduce that particular circuit functionality by converting into the gate level or the lower level of abstractions, in the sense RTL or gate level. Okay, yeah. Simulation times tend to be slower because of the huge number of elements involved into the design. Sometimes simulation things will be less because there will be hundreds of signals. Okay, along with back annotated delay information and hundreds of signals will be there. There are so many delays will be there. Whereas in C program there will be no any delays, right? So, but in Verilog there will be delays. Yeah. Next, placement and routing. Placement and routing is after we are getting the schematic and we have designed the code in a gate level. After everything is fine using the behavioral model, after we are going to read a code that particular relevant code into the data flow or the gate level modeling. Then if everything is fine after doing the gate level verification, the netlist also the hardware schematic also generated. Then we have to place the components and route the components. Placement is the placing the components in a proper way where the area will be optimized, and whereas routing in the sense making connections between the components. The netlist is then inputted to the physical design flow. This is particular thing is related to the physical design flow. Till gate level netlist generation, the thing is everything is front end. Okay, there will be DV engineers, design engineers, verification engineers, architects in the front end department. Whereas in back end department, there will be placement and routing person in it is related to the physical design where automatic place and route will be done. Initially, automatic place and will be route will be done with the help of EDL tools. A good example of such tools is Cadence and Coder and Synopsys IC compiler. Initially, the placement and the router place and route will be done automatically. So we have to adjust those. Okay. Yeah. This will select and place standard cells into rows, define ball maps for input output, create different metal layers and place buffers to meet timing. So there are so many things like metal layers, buffers, input output. All this will be come in our VLSI subject. Those annual creations, PVL creations will be there. So all this will be done by the placement and routing engineers. Yeah. One of the processes then a layout is generated and usually sent for fabrication. All this stuff is done. Then a layout will be generated. Layout in the sense the end product in the form of circuit in the paper. Okay. After after that that will be sent to the fabrication, like in Taiwan there is fabrication units, right? So those fabrication units, it will be sent. This stage is usually handled by the physical design team who are well versed with technology node physically implementation details. All this will be taken by the physical design team who are going to well versed with the technology node and physical implementation. Listen, those persons will take care of those these signal these things. Okay, let me check, right. One sec. Wait a second. Wait a second. Sorry. Yeah, yeah, nothing. Sorry, guys. Yeah, this is the thing which is the cadence encounter. You can see the name here, cadence encounter. After is everything is fine. If you're gonna give the gate level at least to the what is the thing, to the logically after gate level verification. Okay, what will we do? There will so much of delay, right? Gate level verification is also done. Then we gonna give that particular gate level netlist to the input to the physical design flow. That netlist is given, okay? Netlist in the sense in the form of code. Netlist is also in the form of code only, in which it will be there information like gates, how many numbers of gates will be there, what are those gates and what are those connections. Those will be in the form of description. And after we are going to give it to the encoder, it will generate some layout and we have to do our optimization using some algorithms or by our own. After doing optimizations with, there should be no any uh, disturbance or the functionality mismatch. Okay. Again, if we are going to do any what is this called as any modification, you have to check for the verification. Again, after you getting this particular design, you have to verify if you're gonna make any changes. Okay. Next. Stage 3 validation. It doesn't end here. A sample chip will be fabricated. Okay, I told right by the same semiconductor film sent to third party foundry. So, okay, let semiconductor foundry like TSM, TSMC or sorry TSMC and Global Foundries. Okay, like uh, TSMC is a company where they will gonna fabricate on those chips, right? So we will send that particular layout to this company. This will be take nearly once a year for manufacturing of one particular chip, single chip, sample chip, which is called a sample. We don't gonna print millions of chips at a time without doing the sample. Firstly, we have to sample that particular chip, right? After designing layout, this generation of this one particular chip will take once a year or the 10th year. If you want to take sample chip generation cost will be very high. It means 10th year for one particular sample chip. The sample now goes through post silicon validation process. Post silicon validation process means we're gonna test this particular chip again whether the functionality is okay or not. Where another team of engineers must run different patterns in the sense test cases or the stimulus or the input combinations. So it's a lot more difficult to debug in post silicon validation than pre silicon verification, simply because the level of visibility into in the sense post silicon and validation then pre silicon simplifies the level of visibility. It means we can able to see the particular chip, right, into internal nodes of chip is drastically reduced. More over a million clock cycles would have finished in a second, and tracking back to the exact time of error will be time consuming. If there are any real issues or design bugs found at the stage, then this will have to be fixed in RTL, re-verified, and steps that follow this will have to be performed. In the sense, after completion of that particular chip in a hardware, testing it will give the accurate results. In the sense, we are gonna test that particular chip physically, right? Testing will be give the testing results will be accurate than pre-silicon validations verifications. Okay, yeah, that is obvious, right? If you're going to have a device practically, testing that device practically will gives you more accurate result rather than testing that particular device in the software, right? That's the thing. So if there are any errors or the functionality errors in it, okay, we gonna fix it from the RTL from the beginning itself. Okay, it means that particular 10 CR is wasted. Okay, for the sample chip, if the sample chip functionality is become wrong, in particular 10 CR will be wasted, and we should start our process again, beginning with the RTL verification. If RTL verification also we get uh, wrong, then we have to go to previous step. Like this, we will go to previous step and we will find the problem, whether where is the problem. If everything is fine and the sample chip also is working perfectly, excellently with low power consumption and area and everything, okay, then we gonna What we gonna do? With the 10 CR in investment, starting with 10 CR, they have making a one single sample chip, right? One single sample chip, right? So with the same 10 CR, they gonna make how many millions of transistors, millions of ICs. They gonna make 1 million of ICs, 1 million of ICs, or the 1 lakh of ICs at a time using that particular plans here only. Okay, if they gonna make that particular 1 lakhs of ICs, 1 lakhs of ICs after success of that particular sample IC, if you are gonna multiply this particular 1 lakh, not 10 million, in the sense there will be this. Let me erase. Okay, if you're gonna they produce 10 million, okay, then if they sell that particular product or the IC with 100 rupees, then they will get how much? They will get 10 CR, right? So at one production, they will produce 10 CR, okay, the cost will be equal to the number of ICs produced. If we are going to assume 10 CR ICs for the investment of 10 CR, if they even sell that particular IC with 10 rupees, they will get the profit. How many times? 8 times they will get the profit, right? So at the beginning, they have invested 10 CR on the single sampling chip. And after they have invested the 10 CR, after the success of sampleship, they have invested the 10 CR to make the copies of that sample 10 CR ICs. They just invested. The investment is 20 CR, right? Overall investment is 20 CR. If you're gonna make a 30 CR with external all other factors, okay. So if the person or the company sells that particular 10 CR sample ICs with 10 rupees, each product 10 rupees, they will get how much? How much? 100 CR, right? 100 CR. If you're gonna separate that particular 30 CR from the 100 CR, you will get the 70 CR. And uh, in the rare most worst case, okay, some of the products have been damaged in just 10 CF pieces. Okay, again they will test. They won't test this ICs, and the testing will be also done automatically. Okay, some of the products is been damaged. If you wanna take that investment as 10 CR again, those cost ICs cost is 10 CR. Defective ICs have been uh, with the cost of 10 CR. If you separate this, the profit is 60 CR, right? It means that double the profit, right? In the worst case, that the worst case. In the best case, the profit will be 80 CR. So it means how much? Four times the profit. For 20 CR, the four times the profit, isn't it? So that's why they will invest huge at the beginning for the sample chip. Okay, the championship workouts, then they will get the huge number of projects. That's why the VLS engineer will have a high salary. They most of the companies pay high salary. Most of the companies, okay, yeah, that's the thing. Even though there are multiple steps in design flow, a lot of the design activities usually converted on the optimization. Have been told this point at the beginning, right? So even though design can be done, so but they will concentrate on optimization to optimize area power and delay. Delay should be reduced. delay should be reduced, power should be reduced, area should be reduced. All these things only we are going to work. Okay. Yeah. Let me and verification of RTL in the description of the circuit is important to know all the EDA tools are available to automate the process. Improper usage will lead to inefficient designs. Okay, there are so many EDA tools. We have to use some perfect EDA tools like CAD and Synopsys Guide. All this which has perfect perfect tools like SCAD and Synopsys. We have to use these particular tools only to get the efficient design for us. So, hence the designer has to make conscious choice during the design process. So this is the thing, guys. So I hope I have given a clear idea about the what is the things that are going. So once again, I gonna quick recap. That is, firstly we have to take the requirements from the user and the specification from the user. After taking the specification from the user, the architect will design the architect, and we are gonna check whether what are the components that are already pre-available from in the market. We have to use those components and we have to design the code for the components which are not available in the market. We are gonna design RTL code in the behavioral model for that module, and we're gonna verify that particular code using the TB. After everything is okay, we gonna convert that particular behavioral model design into the RTL or the gate level model, because behavioral model is only discuss about the high level details. It gives some random circuit. So for that functionality, we will convert that particular code into the RTL, and we again perform the verification. If everything is fine, we will generate the gate level netlist. After generating gate level at least we will try to generate the gate level at least using logic sensorize. We will generate the schematic. We will try to optimize the schematic in as much as possible. After optimizing, we will again perform the physical design verification or the gate level verification. Okay, after performing gate level verification, if everything is fine, the layout will be generated. The layout will be generated and will be sent to the fab units, and fab units will be do the sample piece. After doing sample piece, if the sample piece is worked out, then we will make more number of copies of that particular samples and sell it into the market. Okay, this is the whole process. If any step is wrong or if any step is mistaken, then the process will go to the previous step again. If the previous step is also gonna wrong, then the process will go again upwards in the next uh, uh, goes to the previous step again. So if the we get an error in physical design verification, we will go to the physical design. If we get the physical design mistake, we will go to verification. Okay, if we get the error in verification, we go to the design code. If we get the error in design code, we will go to the architect. Okay, if we don't go to the architect, we go till RTL, because architecture is already designed, right? So we have to write the code for that architecture, right? So till RTL engineer or the design engineer, we will go. Okay, we will check upwards whenever there is an error or the misfunctionality of a design. The step will be go to backward and check again. And if it also there they if this problem is also there in the in this particular step, if we have problem, we will go to that previous step. If in that previous step also we have that problem, we will go to previous step again. If we have that previous step in also problem, we will go to previous step till RTL design code designer. We don't go to the architecture again, because the architect have been designed the design, given the architecture, right? So the responsibility is on the RTL engineer or the design engineer to design that particular architecture. So the architecture, if after so many times of doing the things, still the uh, functionality is not proper, then only they will go near the architect. Okay, so then architect will check, and he tries to add any models, or he will check any models, whether any models required to achieve that functionality. He will add those models, or he will remove the models which are unnecessary, and this will continue. Okay, this process will continue. Okay, if the sample piece is wasted, then a whole process will be started from the RTL again. Okay, this is the thing about the ASIC design flow. Thank you guys. Like, share, and subscribe to AK App Logics. This is the third video. It's been so long. Yeah. So, but I'm guaranteed that you guys now able to understand what is ASIC design flow. Yeah. So where we are gonna use that particular language Verilog is while designing the code. Okay, even while writing test bench, we can able to write using the Verilog code, but that test bench will be written in SV. Okay, we are gonna write the code of test bench using the SV. Mostly we prefer Verilog to write the code for the design of the system. Okay, and we can able to write the code in for the test TB also, but we mostly not prefer the Verilog to write the TB code. We prefer the SV, which is system language. Next, after the Verilog, we gonna discuss about the system Verilog. Okay, yeah, stay tuned to this channel, subscribe, like, share, and subscribe, and signing off. AK App Logics.